Hello, and thank you for listening to my talk. My name is Owen Benton. I work at the Max Planck Institute for the Physics of Complex Systems in Germany. I will be describing some of my recent work carried out with my collaborators, Han, Nick and Ludo, about how to realise interesting phases of matter known as Rank-2 Coulomb phases in classical spin systems. If you would like to read more about this work, it will soon be published in Physical Review Letters and is also available on the archive. To give you the take-home message of this talk in one slide, the basic idea is this. We've known for a long time that certain many-body systems exhibit something called a Coulomb phase at low temperature. This is a highly correlated but disordered state of matter whose long-wavelength physics is governed by the fluctuations of an emergent vector field, which obeys Gauss's law, dV equals 0, in the ground state. And we've also known for a while how this phase can be identified in scattering experiments. The smoking gun comes in the form of this bow tie-like singularity called a pinch point that would appear in the scattering response and has a twofold symmetric shape. More recently, it's been appreciated, at least in theory, that you can find more exotic generalizations of a Coulomb phase, where the emergent field describing the long wavelength physics is a rank-2 tensor instead of a vector, and it obeys a tensor generalization of Gauss's law. This state has its own signature in scattering experiments in the form of pinch points, but now with a fourfold symmetric structure. What's still missing is some suggestion for how this thing could really emerge in a real material. The message of this talk is that the rank-2 Coulomb phases can appear in relatively simple and realistic models. So they're not just something in a theorist's imagination, they can really occur in nature. A big part of the motivation to look for these rank-2 Coulomb phases stems from the search for an interesting kind of quasiparticle known as a fracton. The defining feature of a fracton is that it is intrinsically localized. That is to say, it's localized in real space, but unlike other localized particles that we see in condensed matter physics, it's not localized by disorder or by quantum interference or something like that, but rather the localization is an intrinsic property of the particle itself. That localization actually comes from conservation laws that the dynamics of the fracton has to obey. So, for example, we could imagine some particles with a conserved charge, which is not so unusual, but then we could imagine further imposing that the total dipole moment of those charges has to be conserved too. If that was the case, and we tried to move a single isolated charge by itself, we would find that we can't, because that would break the dipole moment conservation law. So the conservation laws actually cause the particle to be immobile. The only way to move a charge while preserving the dipole moment conservation law is to create a new pair of oppositely charged particles nearby. So that's allowed by the conservation laws, but it costs energy. So if we want to keep propagating the fracton, we'd have to pay an energy cost at every step of the way. So at low energies, the fracton really is robustly localized. We can also imagine generalizations of this idea, where instead of having particles which are completely immobile, like fractons, we could have particles which are able to move along one dimension within a higher dimensional system. This would happen, for example, if we had a situation where the conserved charge was a vector, and where we further demanded conservation of the angular charge moment, defined here. With these conservation laws, it would be possible for a single particle to move, but only in the direction parallel to its charge vector, and not perpendicular to it. Such a particle would be confined to one dimension within the higher dimensional system, and this kind of particle is called a linon. You can also imagine further generalizations and examples like planons being confined to planes, etc. The question then is, why would these kind of higher moment conservation laws ever arise? Conservation of dipole moment certainly isn't something we observe normally. Of course, we know that conservation laws are connected with symmetries, so what we're really asking is what kind of symmetry would imply conservation of dipole moment or other higher moments like that. The answer is that these kind of higher moment conservation laws arise naturally if you have U1 gauge symmetries acting on a symmetric tensor gauge field. For example, if we write down a symmetric tensor gauge field like this and demand symmetry under transformations like the one shown there, and then starting from that construct the canonically conjugate electric field, which would also be a tensor, we find that that electric field tensor obeys a tensor Gauss's law like this. Then, starting from this tensor Gauss's law, one can derive the fact that both the total charge in a system and also the total dipole moment are completely determined by boundary integrals. If that's the case, it means that local changes in the bulk of a system can't change the total charge and dipole moment, and so they both must be conserved by local processes. So what we learn from this is that higher moment conservation laws, and therefore the existence of fractons, are intimately connected to gauge symmetries of higher rank tensor gauge fields, and that if we can find a system described by this kind of tensor gauge theory, then fractons should follow naturally. In actual fact, there's more than one way of writing down a theory of U1 tensor gauge fields. At a basic level, one can distinguish 4 different cases covered in this very nice paper by Michael Pretko. Those 4 cases can be distinguished based on whether electric charge is a scalar or a vector, and whether or not the theory imposes any condition on the trace of the electric field tensor. So, for example, we can have the case I just showed you, which would be called the traceful scalar charge case, in which electric charges would indeed be fractons. We could also have the same thing, but with an additional constraint that the trace of E vanishes, in which case the charges are still fractons. Alternatively, we could have a case where charge is a vector and the relevant Gauss's law is a first derivative of the electric field tensor. And if we have that theory without any constraint on trace E, then the charges are actually line-ons, able to move only along the direction of their charge vector. Or finally, we can have the vector charge theory, but with the additional constraint that trace E vanishes, in which case the electric charges are once again completely immobile fractons. Our contribution in our recent work is to show a simple classical spin model which realizes the vector charge traceless theory at low temperature. I'll also show you briefly at the end of the talk that we can also write down a model realizing the vector charged trace-full case. As I just said, the model we've constructed is a classical spin model. Now, you might wonder why we spend time constructing a classical spin model rather than the quantum one. After all, the goal is to be able to move towards experimental realizations, and real spins are quantum spins. So I want to spend a moment motivating why constructing a classical spin model is an interesting and worthwhile endeavour. Firstly, with classical spins it's much easier to get an analytically tractable description which allows us to make progress faster. Secondly, numerical simulation of classical spins avoids a lot of difficulties associated with quantum spin systems, Monte Carlo sign problems, and the like. So once we've made a prediction for a novel phase of classical spins using our analytic approaches, we can very readily verify that prediction in simulation. Also, even though real spin systems are quantum and not classical, classical spin systems are nevertheless often a reasonable approximation of the behaviour of quantum ones at finite temperature. So if we can find some interesting behaviour in the classical spin model, it may well also be present in some corresponding quantum system, and so our classical model still suggests routes to realization. And finally, if we find some interesting classical spin liquid phase, this can be a kind of parent phase to quantum spin liquids, which would appear if we were to add quantum fluctuations back into the problem. So these things make the classical spin problem a very good starting point for study. The construction of our model begins by thinking about a very well-studied model, the nearest neighbour classical Heisenberg model on the PRL lattice, which is this network of corner-sharing tetrahedra. To study this Heisenberg model, it turns out to be very useful to rewrite the problem in terms of 4 fields defined on each tetrahedron. M, the magnetization of a tetrahedron, and 3 fluxes, which we will call E alpha, with 1 flux being defined for each of the 3 spin components. Written in these terms, the Hamiltonian only depends directly on M, with the result that in the ground state M must vanish on every tetrahedron. The fluxes E, meanwhile, are free to fluctuate. To construct a low-temperature theory of the system, we need to think about how to deal with those fluctuations in the presence of the strong constraint that M must vanish everywhere. Fluctuations of E are correlated because neighbouring tetrahedra share a spin, so the fluctuations of E have to coordinate in space in order to avoid inducing violations of the m=0 constraint on their neighbouring tetrahedra. Theoretically, we can deal with this in the following way. First, we divide the lattice into 2 species of tetrahedra, A and B, like so that each A tetrahedron neighbours only B tetrahedra, and vice versa. We can then independently place all the A tetrahedra in a ground state. The constraint that m=0, as applied to the B tetrahedra, then becomes a constraint on how E is allowed to vary between A tetrahedra. Using a gradient expansion, we can turn that into a constraint on the spatial derivatives of E, and once we've done that, the outcome is that each of the 3 fluxes independently obeys its own Gauss's law. This gives us essentially 3 copies of an ordinary Coulomb phase with 3 vector fluxes, 1 for each E. So from this we can derive a low-temperature theory of the classical Heisenberg model on the PRL lattice. We have separate Gauss laws operating on each of the 3 flux fields, and each contributes a separate E² term to the free energy. Using these equations, we can then calculate correlation functions in momentum space for the fields E, and they have these bow tie-shaped pinch point singularities. So this Heisenberg model gives us an ordinary Coulomb phase, in fact 3 copies of an ordinary Coulomb phase, but what we want is to turn that into a rank-2 Coulomb phase. In order to see how to do that, it's helpful to combine the 3 flux vectors into one matrix, with each vector being 1 column of the matrix. In that language, the 3 Gauss's laws combine into one tensor equation, which looks exactly like the Gauss's law for a vector-charged rank-2 electromagnetism. The matrix E that we have here can quite generically be decomposed into a symmetric traceless part, an antisymmetric part, and the trace multiplied by the identity matrix. As it is at the moment, this does not describe a rank-2 Coulomb phase because the matrix is asymmetric and the columns are linearly independent of each other. But if we can get rid of the antisymmetric and trace contributions to the E matrix, then we will have a traceless rank-2 Coulomb phase. But we have to do that without changing the form of the Gauss's law constraint. So, how can we do that? Well, if we remember how we did our coarse graining construction, which led to our 3 copies of a Coulomb phase, we'll remember that the entries of the flux matrix come from the A tetrahedra, and the Gauss's law comes from the interaction on the B tetrahedra, at least within our construction. So we're going to write down a new Hamiltonian, where the Hamiltonian on the B tetrahedra is exactly the same as it was before, and will therefore preserve the same Gauss's law, but we'll add terms on the A tetrahedra which exert an energy cost for having finite trace and antisymmetric parts of E. And this will give us what we want. At low temperatures, the additional terms on the A tetrahedra will force E to be symmetric and traceless, and the interactions on the B tetrahedra will impose a Gauss's law of the form of appropriate to vector charges. In this new construction, the symmetry between A and B tetrahedra is clearly lost. which means we're actually working on a slightly altered lattice known as the breathing pyrocle lattice with broken inversion symmetry. You can see in the picture here, the breathing pyrocle lattice has one species of tetrahedra of a slightly different size than the other species. This is a real lattice that exists in many materials in nature. The interesting thing is then that we can reconvert our new Hamiltonian, which is in terms of m's and e's, back into one written in terms of the original spins. And when we do that, the outcome is surprisingly simple. It only involves Heisenberg and Jalaszynski-Maria interactions, which are very common types of spin-spin interaction. So our construction has given us a simple spin model, which, based on our analytic arguments, should yield a rank-2 Coulomb phase at low temperature. We now want to check this using numerics to see if it really works. And there's a clear test we can apply to check that, thanks to the results in this paper by Pren and collaborators. They showed that while in an ordinary Coulomb phase, the correlations of the flux matrix should have these twofold pinch point structures, in a rank-2 Coulomb phase, you should see fourfold pinch points, like this picture on the right. So what we need to do is plug our model into some classical Monte Carlo simulations and see if we can find some fourfold pinch points, which would be a clear signature of rank-2 Coulomb phase physics. And, lo and behold, when we do that, the Monte Carlo simulations indeed show these fourfold pinch point structures in the correlations of the flux matrix, demonstrating that the simulations really find a rank-2 Coulomb phase for those parameters where we would expect it and at sufficiently low temperature. We've also used Monte Carlo simulation to look at the full phase diagram of our model, varying the strength of the Jalaszynski-Maria interaction and the temperature. The green region of the phase diagram shown here, on the side with negative dm interactions, is where we find the rank-2 Coulomb spin liquid. We should note that at very low temperature, and I mean very low indeed, noting the logarithmic scale on the temperature axis, there is a magnetically ordered phase below the rank-2 Coulomb phase. Nevertheless, although the rank-2 Coulomb phase does not extend down all the way to zero temperature, there is an extended region of the phase diagram in dm interaction and temperature where the rank-2 Coulomb phase physics is observable. So the natural next question is, could this really happen in a real material? Well, we don't have a definitive realization yet, but there is some good reason to be encouraged that yes, it could happen. In the material barium ytterbium zinc oxide, the ytterbium 3+ ions form a breathing pyrocle lattice with strong interactions on the A tetrahedra and weak interactions on the B tetrahedra. Experimentalists have been able to determine the interactions on the A tetrahedra, and they have exactly the form we need: antiferromagnetic Heisenberg exchange and dm interactions with a negative coefficient. What's missing is that we don't know what the interactions on the B tetrahedra are like, although they seem to be very weak. But if there are interactions on the B tetrahedra, and if they are dominated by antiferromagnetic Heisenberg exchange, then we'd have everything necessary to realise a rank-2 Coulomb phase. This gives us some encouragement that the rank-2 Coulomb phase could be realised, possibly in this material, or perhaps more likely in closely related materials belonging to the same family. If we're hoping to find real rank-2 Coulomb phases in experiment, it becomes important to know how we would actually recognise them in a realistic experimental setup. In simulation, it's easy to find the fourfold pinch points which serve as a smoking gun for this phase, because we can choose to measure any correlation function we want. In experiment, we're limited to measuring correlation functions which couple directly to the probe we're using, and it's not necessarily trivial to isolate the part of the signal which uniquely reveals the rank-2 Coulomb phase. Nevertheless, it is possible to isolate the fourfold pinch points in neutron scattering experiments by using polarized neutron scattering and making a careful choice of scattering plane and Brillouin zone center to measure around. The plots on this slide show a prediction for the neutron scattering structure factor in the spin flip channel of such a neutron scattering experiment, and the fourfold pinch points can be clearly identified. This kind of experiment can be used as a test for the existence of a rank-2 Coulomb phase. So far, I've shown you a model which can realise one particular kind of rank-2 Coulomb phase, the vector-charged traceless version. But as I showed you at the beginning, there are other kinds too, and it's interesting to try and generalise our method to construct the others. This is possible in at least one case. We've managed to construct a model realising the traceful vector-charged rank-2 Coulomb phase, for which the electric charges would be line-ons instead of fractons, again starting by perturbing a Heisenberg model. The construction for the model for this phase is very similar to what I already showed you, but this time we simply leave out the term that would force the trace of E to be 0. Unfortunately, this time when we convert back from a Hamiltonian in terms of M's and E's to one directly in terms of spins, it ends up looking rather more complicated than before. So this model for the vector-charged traceful case doesn't seem quite so close to something that could be found in experiment, but it at least establishes a firm model to study the properties of this phase on the lattice. So, with these results, we've established classical spin models realising 2 out of 4 of these rank-2 Coulomb phases. And with that, I'll just summarise as I come to the end. We've developed a method for constructing general forms of classical spin liquid, allowing us to examine more exotic spin liquids, including rank-2 Coulomb phases. We can use this method to construct realistic models for rank-2 Coulomb phases, which could lead to the realisation of fractons in the laboratory. And these phases can exist in real materials and can be identified by searching for fourfold pinch points in polarised neutron scattering. And with that, I will thank you very much for listening.